So I wanted to finish this topic about external forces. So where we stopped last time is that we considered that the whole system is divided by the system to which we're looking at. So Q, which is described by the vector Q, and the rest is described by vector Q capital, which gives you the Lagrangian which has a form of the system, kinetic energy of the rest, kinetic energy of the rest plus minus potential of interaction within the system minus potential of the interaction outside and minus potential of interaction between the system and the rest. And if you write, so the Lagrangian function of the system just composed of what is or functions of coordinates q, and then the equation of motion takes the form of the Lagrangian equation, where the left part hand side is just usual or the Lagrangian expression, but taking the Lagrangian function of the system, and then on the right we put what is called external force, and this is minus of the interaction potential with respect derivative with respect to coordinates. So this is a general equation of motion for the system, which is not assuming the system is isolated, that there is an interaction which we have to define, and essentially this have to be modeled. So we need a model for this. For the rest, and then you have equation of motion which you can solve. So some examples we saw. So the example which is a very important example that we will consider is a dissipative force. For example, friction. This kind of friction, it can be. Well, there are different ways of how you can dissipate. So essentially, what is dissipative force? It means that the energy is passing from the energy is moved from macroscopic degrees of motion so Q describes macroscopic degrees of motion, the position of the like the full body, so like center of mass, to microscopic degrees motion, which is given by the other vector. So like motion of particles within the same body. Often it takes form of the heat generation, because heat is exactly when something is getting warmer. It means that the microscopic motion gets stronger, so energy is transported there. So the total energy is conserved, but it can be moved from one part to another, and in particular, it can be moved from the part that we describe to the part which we don't. Okay, so we can write as there is a standard model that works in many situations that you can describe this external force. You do it from a couple of simple arguments. So the first of all, So we will call this dissipative force as F dissipative. So this is external force. So F. So it's not that much external because it's within the same body, but from this point of view, it's external because it's external with respect to our description of the system. So what you can say about this dissipative force is that it's exactly zero. Well, in usual models, it's exactly zero when there is no motion. So if we're at rest, it's reasonable in many cases assume that there is no force. So only friction only occurs when there is motion. And the next is that, so if it's zero at small force, then we can model then we can take just linear, which is linear Taylor approximation. Which means that if dissipative force is zero at zero velocity, then what we can say that dissipative force is linear in velocities, right? So usually the general expression will be the Taylor series, but then the approximation just takes part. You neglect the rest. So what is written here, D should be, so Q, remember Q dot is a vector. So it's a vector of Q1, Qn dots. So it's n by 1, right? So it's column vector, which means that this is also column vector. So if you want to put linear relation between the two, you can multiply the vector by a matrix, which should be square, n by n matrix. So D is n by n matrix, right? So now D is D is n by n matrix. And D is a metric which in principle may depend on everything, right? So it's the standard, the usual model, they just say that we assume that D is just function of position, or constant, or just function of position. So whenever you have these two assumptions, and you use Taylor expansion, and it's and the coefficient depend on the position, so then you have a model for your external dissipative force, which would be let's put minus here, because minus is just to point out that the force is always resisting to your motion. So if you move forward, the force usually looks backwards. So it's minus dq. So this is typical model for dissipative force. Sometimes called viscous dissipation, or well, it's many. There are many names to this. Depends on the physical situation. So what is important? So the properties. So one very non-trivial property is that this matrix, which is n by n matrix, is symmetric. So if you transpose it, it will be the same matrix. And this is quite non-trivial because in principle from mechanical consideration you don't see it directly. And this is a rather distinguished result from statistical mechanics. So if you want to derive this result, you have to go really deep into the motion of particles within the body, and from certain considering microscopic motion, you can derive that whenever you, for macroscopic quantities, you have this force, the matrix will be symmetric. Yeah, so that's not trivial. And the second condition is under the first condition, the second will be natural. So we will see why it's natural. So the second condition is that the matrix is positive definite. Positive definite means that whenever you take this product, so what does this product mean? So you see this is a vector, right? N by 1, D is a matrix, N by N, and Q transposed is a vector, but it's horizontal, the row vector, 1 by N. So whenever you multiply all of them, it becomes just a number. Okay? So this is, so the positive definiteness means that this is always positive if, unless velocity is 0. So it tells you that there is always, so we will see right now what this means. So let's see what it means. So if you want to understand what it means, let us consider the change of energy. So we define the energy of the system in the usual way as we do. So whenever you have a Lagrangian function of the system, when you define energy of the system, it's not necessarily, actually, it will not conserve anymore, but we will just use exactly the same formula for the energy that we usually define. So remember, the energy was defined as sum of all components dl by the velocity minus L. So this was expression for the energy for the full system, which is conserved. And this is the energy of our system, which is not isolated. It's not conserved, but we just use exactly the same expression. And you know that you can just show that it's the same. You will have, in the same way, it will be sum of the kinetic potential energy. So now let's show that, let's see how the energy changes under this force. So what we have? So first of all, equation of motion. So Euler-Lagrange equation for our system is this one. So let's just repeat this equation. On the right-hand side, we have the dissipative force. So it's written for the is component, right? So we put just is component of this vector, because this is a vector. And this is for all components. So this is the equation of motion. This is energy. So let's see how the energy of the system will change. So change of energy is derivative. So we have to differentiate it with respect to time along the trajectory. Right? Along the trajectory. So we'd have to differentiate this full expression. Oh, sorry. I'll just recall you that this depends on coordinates. So this is what we do, and we have to differentiate it with respect to time. So this is energy by definition. So what we do, first we differentiate the first term separately, the left side and the right side. So we take derivative of the first term, right? And then derivative of the second. Derivative of the second, you add a dot, right? And then what we do, we have to differentiate with respect to coordinates and with respect to velocities and then with respect to time. So we already have a sum, so we use the same sum. It will be dl as dqi, qi dot. So this is with respect to components of the vector q, and now with respect to components of the other vector. qi and then second dot with respect to. And this is within the same sum. So now you see that this cancels with this. And these terms together we can express from the upper expression. So these terms together give us minus sum of all components dq dot. Well, let's just make one more step. Otherwise, it will not be clear. So it's what left is this d dt dl dqi dot. We can put it together with the other one. Like this. Now, from equation of motion, we know that this is d minus d dot. No, dqi. So then it becomes a sum with a minus. I just put them in a different order. And this is just scalar product of the two vectors, which you can write as minus q dot d q dot. Okay, so that's exactly the expression this is n transpose. So that's exactly that expression that we considered before. So you see that the result is that the result is the change of energy is exactly this expression. And it's negative, right, if there is motion. So now you see the y positive definite condition is applied. It just ensures that whenever you have dissipative force, it always takes energy from the system. See, so it's the change of energy is always negative, unless unless there is no motion. So whatever motion system does, there is always friction. So that's a condition of positive definiteness of the matrix D. So this is what's called dissipation. So the system always loses the energy, which goes to the rest of the degrees of freedom. So what you may encounter in this kind of studies is the definition of what is a Rayleigh dissipation function. So it's a function which depends on coordinates velocity, and it's just defined as 1/2 q dot t d q dot. This expression, but without minus and with 1/2. So it's usually called Rayleigh dissipation function. So that how it's used. So first of all, from then you can just write all the equations in a more compact form. So Rayleigh function minus 2 Rayleigh's function gives you change of energy, and the reason why it is the motivation of the definition is that dissipative force can be written, you see, as minus derivative. So each component can be written as minus derivative of the Rayleigh function with respect to corresponding velocity. So just show that can be exercise for you. So we will do in next classes many of this kind. So I keep it an exercise. So just show that whenever you differentiate this with respect to velocity, because velocity comes in both sides, 1/2 will disappear, and then you will exactly get this minus d q dot. So that's motivation in the sense. So you see that Rayleigh function, it's kind of a potential function for dissipation, but potential. If you get usual forces by differentiating with respect to coordinates, then dissipative force you get from Rayleigh function to taking derivative with respect to velocities. So that's analogy. There's not much deeper about this, just putting a formal analogy between the two. So that's dissipative force. That we will use it a lot because this is it usually appears in most physically interesting situations. Okay. So we are done with with the first part of the course, which is mechanics. So the next part, which is the largest one, it's oscillations. Oscillations, so I don't have, as I said already several times, so I don't have PDF notes, type notes for the beginning of this section, but there is PDF about the final part of it. So the beginning will be only, so if you want to refresh, you just see the lectures. Okay, so what is it about? So oscillation is, so we have equation, so we know now how to write equation of motion, at least in principle. So imagine you write equation of motion. So next step is to solve. And it turns out that solving this equation of motion is a very complicated problem. It's a very complicated problem. In general, it's not solvable. So in general, you just cannot solve unless you can do it numerically. But even if you can do it numerically, it's still, okay, you get a collection of data. It still doesn't mean that you understand what happens. Right? So you just, numerically, you can probably predict what happens at certain interval of time, but it's even if you cannot solve equations, it's good to understand what are the general properties of their solutions. Right? So understand something, at least qualitatively, what is the typical behavior of the solution, or typical form of the solution, why it happens, and so on. So this is This is our second goal. In general, you cannot do it. And there are a huge amount of open questions in this area, essentially because even with a system with finite number of coordinates, this system typically have chaotic behavior. And the chaotic behavior is, well, we understand much about this, but we also don't understand much about this. So you know that in IMPA, especially known for the area of dynamical system, the area of dynamical system is exactly how to understand what is the typical behavior of the solutions of differential equations. So in particular, these differential equations that we consider. And apart from some situations, we don't understand what happens. Okay, so oscillations is just sub part of this theory, which is dealing with small motions. So you cannot describe the general motion, but in a situation where the motion is kind of restricted, so whenever you have like something which is almost in equilibrium but just vibrating a little bit, the equation becomes simpler because you have small parameter. So your motion is just, you know the position of equilibrium, so you know the system can just stay without the motion, but then you want to consider what happens if the motion will be small. So this is a simpler problem just because motion is small, so you can use Taylor expansion. So you can use perturbative techniques, and this gives you a lot of technique at hand that you can apply. And this is what we will do. So our goal will be to consider small motion. But before considering small motion, we can study the one situation when we can really understand everything. And this is a situation with 1 degree of freedom. So today we start with a system with 1 degree of freedom. Degree of freedom, so this vector q, it has n components, so they are called degrees of freedom. So in general, vector q is n-dimensional, so we have n degrees of freedom. So now we will consider this situation with 1 degree of freedom. So the vector q, which we'll just consider as a coordinate on a line, is a real number. So that's essentially the only situation when we have complete theory. So already with number 2, we are in trouble. In general. And in general, with n degrees of freedom, we know even less, but the theory of small oscillations is rather complete. So we start with 1 degree of freedom, and we try to solve it just completely. So we have a Lagrangian equation. So this is a Lagrangian function of our system, and we don't consider any more closed systems. So there are so we consider the system, but we consider the system when the forces that apply to the system are potential. So you can put potential U. So for example, gravitation or elastic force, etc. So we will consider a system with 1 degree of freedom, where all the forces are, first of all the forces are the ones which can be written as a potential. The second step, we can add external force, for example, dissipative force. So this is a Lagrangian that we start consider. We'll see examples. So that's situation which we can study from beginning to the end, essentially. So in this case, what you have, in this case, there is no time, which means that the system conserves energy, right? And energy is, you have to replace minus by plus. So why it conserves energy? Because Lagrange does not depend on time. So we have a symmetry. We have continuous symmetry, which is homogeneity of time, so time translations. And automatically we have a conservation of energy. Now, if U is not a constant, then we don't have translation in space. Right? So translation in space is not there. So we don't have homogeneity in space. So there is no momentum conservation. So when U is not constant. So when U is not constant, there is no Lagrangian is not invariant with respect to change of coordinates in space, so there is no momentum conservation. Okay, so Lagrangian is here. So we next step we write equation of motion. So which is Euler-Lagrange equation? And you already know what it will be. So it gives you, the first term gives you mass by acceleration. It's Newton's law. And the second term, which you can put on the right, which gives you the force. So this is a force, kind of internal force. And then afterwards, we can also add extra force here, which will be external. So how will we do? So now we can divide both sides by the mass. And we can just write it, this equation is in this form. So f of x, in this case, is 1 over m minus 1 over m du dx. So equation of motion for the system with 1 degree of freedom is that acceleration equals something. Essentially, this is a force normalized by mass. So how do you solve this equation? How you solve the equation? You go to phase space. Phase space is a space where one coordinate is just x, another coordinate x dot. So usually that x dot, we just call it y. So let's just separately consider coordinates and velocities as two different coordinates on a plane. So what then you have? So you can write, first you take definition of y, you can flip. And then you can write this equation, because this is second derivative of x, which is first derivative of y. F of x. And this becomes a system, which is equivalent to the first equation. But now it's a system of two ordinary differential equations on a plane. Right? On a plane. So that's often called canonical form of ordinary differential equation. You started with differential equation of higher order, and you can just reduce it to the first order, but two equations. And this equation gives you the law of motion on a phase plane where, let's take coordinate, horizontal coordinate x, vertical coordinate velocity. So at each point of this plane, you get a vector, which is the right-hand side of this system. So this vector, which is y f of x. And it tells you that change of x and y is in this direction. So there is a vector at every point. So there is a vector space, vector field on a plane. And from this equation just tells you that the solution, whenever you have initial point, some initial velocity and coordinate at certain time, at time t0, then whatever motion you will have, at every point, the derivative should be exactly the vector from this vector space. So any solution should always just follow these vectors which fill the phase space. And the full solution is given by the theory of ordinary differential equations, which is in principle one of the courses of IMPER. So I will not give a rigorous formulation. I just tell you the idea is that if potential, which is coming here in the right-hand side, is sufficiently regular, which means smooth. So it means that if this function has sufficiently many derivatives, so we can one derivative is already necessary to make sense of the equations. So if it's sufficiently regular, smooth, or there are other formulations that mention regular, then there exists a unique solution of this system, for any given initial condition. At initial time. So whenever you put initial point, you say at time t0, I'm here. The rest you know. And the theory usually tell you that there is a unique solution, at least locally in time. Also, you put some regularity condition that it exists at every time. Because the difference is that sometimes the vector field is such that you can go to infinity at certain finite time. But anyway, so idea is that system with 1 degree of freedom is fully described whenever you give its motion is fully described whenever you give initial point, and initial point means coordinate and velocity. So the two things are necessary: coordinates and velocity. Whenever you have coordinates and velocity, you have a solution. Okay. So now, certainly, the next point that we will do is, let's say the theory of oscillations is about motion around equilibrium. So let's apply this concept here first. So let's first consider the concept of what is equilibrium. Equilibrium is a solution which doesn't change in time. Right? So you stay at the same point forever. So whenever a solution is constant, automatically the y, which is x dot, is 0. Right? So the equilibrium must be always on a horizontal x. So equilibrium is a point on x. and y is 0 means that its derivative is 0, then f is 0. So y is 0 means f of at this point is 0. Now remember that f is derivative of the potential, means that potential derivative is 0. And this is already important. So equilibrium, so all equilibria are extremal points of the potential. So equilibrium is whatever point of u where derivative is 0. All these properties then will be extended to the n dimension, n degrees of freedom. So the next step is, okay, we have equilibrium, which means that if you start at this point, you continue at this point forever. But now the next question, what happens if you start nearby? So at nearby, what will be your motion? So let's consider motion which is near the point x0, so it means that you have the difference between point and equilibrium is small. So what will happen nearby? And now let's try to see the solution of this equation near this point. So what you have in this case, we have, so first of all, what is the potential around this point? The potential we can expand in Taylor around equilibrium. So let's take Taylor expansion. The first term will be constant. Then there will be derivative. It will be second derivative with 1/2. And so on. So next term will be cubic. Okay. So this is Taylor expansion, assuming that all so it's smooth functions, so we can differentiate. So this is the approximation of the potential near this point. Okay, and then we know that this is 0. Okay, so this is exactly condition that we have an equilibrium. So we have first, this is 0. This is 0. Okay, so then the function f, which you have in this system, is 1 over m du dx. So this is constant. So the first term which is important is this, taking derivative with respect to s cancels 2. So it will be minus. So let's call this number a. Yeah, this number a. So we call a to be second derivative of u at equilibrium. So that's a constant. So this will be minus a over m delta x, and then second order term. Right, so we differentiate. It comes from this term, this a by 2. This 2 cancels. M comes from here, minus delta x in the next term. Agree, no? Okay. And then you use this function in the equation of motion. So you have acceleration. We can put delta because subtracting x0 into the derivative doesn't change anything. And this is equal to f x, which is this? So neglecting, So we're close to equilibrium. So this is small. This is even smaller. So we can neglect this, and we take local dynamics. Next term we put on the left. So we have local dynamics described approximately by this expression. And we can do the same with the energy and consider what is the energy expression near the equilibrium. Energy is a function of coordinates and velocities, so it will be mx dot square over 2 plus u over x, and we use this expression. It will be, so at equilibrium this is 0. So also we take Taylor near x0, 0. Yeah, because velocity is 0 at equilibrium. So velocity we just keep the same. On velocity we can put delta x dot, right? Doesn't matter. Because difference, you can put minus x0 into the derivative. And then for you use this whole stuff. So it will be plus u0 plus a over 2 delta x squared plus x cubed. So you can also approximate energy by neglecting this piece. So we have equation near the equilibrium, and we have energy near the equilibrium. So with these two pieces, we can describe local dynamics completely, and we do it after coffee. So break. Well, so just idea that we have a monitor, Antoine, and his email is on my web page. So if you enter alexei.impo.br, then there is kind of some information about the course where I put lists, exercises, and that's it. And then you have find name of Antoine. So his name Antoine. He speaks English, French, and Portuguese, and maybe something else. Just so all questions you can send to him, whatever you have, and also if you want to mark some time, this is also possible. No? So if there will be some critical mass of people who, I think the easiest is just directly communicating. Antoine is sitting at the room 108 downstairs. This is Laboratory of Fluid Dynamics, which is also written on my webpage. So you can just come directly talk to him, and if there will be some critical mass of people, which I doubt, then you can mark the time, special time when you can discuss. Or probably later, at the end of the course, you can discuss all the exercises and so on. So the idea of exercise will be that you either bring to me in a paper or you send them by email. Then there will be some corrections. And then if your objections are very welcome to the corrections, but also with an arguments. So usually, well, I think that the exercises will be all the time until the end of the course, and then probably at the week after the carnival, you can see all exercises, and maybe it's good to have one of the classes. Let's make this exact. So probably one of the after the carnival we will only have. Oh, by the way, it's Monday, Tuesday, carnival. So the carnival 2021-22 is a carnival, right? So we don't work. And then there will be 27, 28, and 1st of March. 8 and 1st of March. So let's do it like this. So let's maybe we put on 28th of February so it doesn't pass it to March, and make the exam on this day. Is it okay? Just time of the class, maybe it will extend a little bit. So it will be considerable problem we can reconsider, but I think that we can fix it. And then 1st of March. You can talk about a final exercise, revisions. So you can give final objections and whatever you disliked from our side, and so that's how we do it. No, okay. Yeah. So I'll make a photo of this. I think. Let me check if yeah, February 2023, 27, 28. Good. So that's a plan. And February. So the week before that, it's a carnival. So you dance and prepare for the exam. Exam will be written. So I will give different questions about all the topics. You can during exam you can use your notes. So it will. I don't know if you can use the notes. We will decide about this. I let to use. Depends on if it will, if we succeed to do it very simple. We will see. So we will agree about this in February. Okay. So thank you, Antoine, for coming. So you saw. Okay. So. Good. So let's continue. So what we do now is is solving this equation. So there is case 1. So there are different cases which, as already you noted, it will depend on A. So the only parameter which is new parameter which comes here is A. So there are 3 cases: A positive, A negative, and A 0. So case 1 is A positive. A positive means that the second derivative of the potential at the equilibrium is positive. Okay, so in this case, A over M is positive. So we can say that A divided by M is a square of some number, which we call omega. It will be frequency. And then our equation of motion can be written as delta x double dot plus omega squared delta x equals 0. And this is the equation that you may know how to solve. So general solution. So all solutions of this equation can be written as some constant multiplied by cosine omega t plus another constant phi. So the two constants, c is arbitrary real constant and phi is arbitrary angle. So it's modulo 2 pi. So what you can check is an exercise. So in an exercise you can check that there exist unique constants. So there are two constants. They're uniquely defined for any given initial condition. And initial condition means that if you're given velocity and position and coordinates, coordinates and velocity at any time, then it's uniquely defines two coefficients, and then you have a solution. So what the solution is? So whenever we have a solution delta x in this form, then you can also define. So delta x, let's repeat, delta x of t is c cosine omega t plus phi, and then you find velocity. It's minus c omega sine omega t plus phi. Right? So all together they give an ellipse on a plane delta x dot. So let's see why. No, not see why. Let's how it looks like. First, on the phase space, so we have an equilibrium which we know it's on the horizontal axis because velocity should be 0. And then what is given by this cosine sign is just ellipse around this point with the center. So certainly x dot is velocity, so you know that this is the direction. It should be positive above when x dot is positive and negative below. So this is our motion general solution of this equation on the phase plane, and you see that this is what you can say is stable equilibrium. We will make this concept rigorous, but for now it's just clear that what you have is that if you start nearby, you will not move away. So you will just whenever point you start, you will be on certain curve which will just move around equilibrium. So why is it so? You can see it also from another reason. Essentially, you can see from energy considerations. So you see that our energy is mx dot square over 2, and the A by m. So there is A there, right? So A. Let's put m outside. M will be x dot square over 2 plus omega squared delta x dot square. So this is our energy, approximately. Or we can just make it exact. So that's expression for energy. So what you can see, if you plot energy as a function of x, so we have an equilibrium somewhere here, 0. This is our energy at the equilibrium. And then from this, sorry. This, right? So this is U0. This is our energy at the equilibrium, because in equilibrium there is no velocity and the rest is 0. And then around the equilibrium, the energy is described by the sum of squares, which means that that's locally, this point is minimum. And essentially what these curves are the cross-section so the level is just a level curve of energy, because energy is conserved. So this is what I erase here. We know that energy is conserved. So the motion will be on the level curve of this surface, and the level curve of the surface. So any level curve of the surface around minimum is approximately ellipse. So so the fact that we have geometry of the orbits on the phase plane is approximately ellipse is because energy has a local minimum with non-zero derivatives, and then any cross-section near the minimum will be in the first approximation ellipse. So this is where this come, and from this consideration we have more, because so what we found here is that locally all trajectories are closed. So whenever you come from point, you come to the same point after that. But this was approximate. So now we know that it's exact, because whenever you cross the surface by constant energy plane, you get closed orbits. So even if you consider corrections, so exact dynamics is also exact. So exact dynamics is not exactly ellipse. It will be deformed a little bit, but it still will be closed. So we know that all orbits will be closed. So that's a stable situation. The second situation is when A is negative. A is negative, and then we can, A divided by M is negative, and we can say that minus A over M becomes positive, and we call it sigma squared. An equation becomes the same, but with a minus. This is approximate. With a minus here. And also we know the general solution. The general solution is the delta x. So you know that the solution is exponential with sigma time and minus sigma time. So the general solution is the sum of any coefficient but exponential sigma t plus any coefficient by exponential minus sigma t. So second derivative always gives sigma square in both cases, right? It cancels with the second, with the for any a, b real numbers. And then you can get velocity just by taking derivative. It will be a sigma e sigma t. Here will be minus b sigma e minus sigma t. So this is general solution. And again, you can check that whatever initial condition you give, you can always find uniquely a and b that give you the solution. And now let's see how it looks like on a phase plane. So first, let's consider the solution when, for example, b is 0. Assume that b is 0 first. So first solution will be when b is 0. And a is some number. So a is not 0. So what you see is that coordinate velocities, they are proportional to each other. Right? So it will be a straight line. Here, a straight line. Okay, so that's the solution. Now, when b is when a is 0, it will be also a straight line, but with a minus, just symmetrically. So that part is when b is, when part is, so that part is b is positive, and this part is b is negative. And then there are situations where, so above, so there will be this curve which correspond to, so derivative should be always positive, so it's so it should be a, so that the x changes the sign. So a positive. I think like this. Let's write. When a positive and b negative, then it gives a plus plus, and its derivative is positive. Okay. That's correct. This will vice versa. And then there is so here everything should be negative. Here everything should be positive. Okay, so depending on signs, you get all the curves. And the curves which you get from this expression is hyperbolas. So where this was ellipses, this is hyperbolas. Except for the straight lines we just come close. And also what you can say, so x dot is velocity, right? So it's positive on the upper part, so you can draw the arrows. It's always going right on the upper parts. And it always goes left on the lower parts. Somehow, along these curves, the arrow is consistent. You just pass through the point. Here it's also consistent. The only inconsistent is on the straight lines, because somehow the motion is outwards along this line in both directions and inwards in this direction. And now let's do the same plot for the energy to see where this comes from. So the energy now is what? The energy now is u at x0. Then there is this expression. Forgot to. This expression. So our equilibrium is somewhere here. Then this is, let's say, u0, u at x0. This is so this is extremal point of the energy. So derivatives both with respect to coordinates and velocities are 0. But now in velocities, it's increasing function. In coordinates, it's decreasing function. So how to plot it? So let's first, well, I will draw, but you probably, let's see if it will work. So that's a function which increasing in velocities, but decreasing in coordinates. So that's what's called saddle. And equilibrium is saddle point. So it's a surface which is increasing in one direction and decreasing in another direction. And now, if you make our trajectories are the constant energy surface, the cuts of the energy surface with a constant value. So this the surface line. So for example, at energy positive, it gives you these lines, for example, and energy negative, energy bigger than minimum, and the energy which is constant smaller than minimum, and the minimum than extremum. It gives you these cuts. Essentially, whenever you have a saddle point, so which is increasing in one direction, decreasing in another direction, every cut will be approximately a hyperbola. So this is a reason. And whenever you cut it exactly through minimum, you will get straight lines approximately. So just take a saddle and try to cut it through the take a saddle and try to cut it exactly through saddle point. You get two straight lines in the first approximation. Which are these lines? So essentially, this picture is universality. It comes from the universality, local universality for the form of the cuts from the saddle surface. So whatever saddle surface you get, which is extremal point, but it's minimum with respect to speeds, but maximum with respect to coordinates. Every level curve around, nearby will have the form either hyperbolas, or if you cut it exactly through the point, it will give straight line. And this is, of course, the situation with unstable equilibrium. Unstable because whatever point nearby you take, you will go far away. And you will not oscillate. So you take any point, you are in any one of the curves. So generally, unless you are right here on this unless you're on this line which exactly comes to the center, any other line will draw you away. You can, in principle, you can sometime at certain moment come closer, but anyway, you will be drawn away from the equilibrium. So it's an unstable situation. So the case 3 is A equals 0. Well, you can try to solve this equation with A equals 0. Then delta x is constant plus another constant by time. But in principle, this doesn't tell you much, because when A equals 0, it means that this term is 0. So everything is given by the next term. So you have to continue expansion. So higher order derivatives of the potential, in that case especially the third order derivative, first of all, must be considered. And we will have a more rigorous expression which tells about what happens in this situation. So I will not get deeper. The only comment is that these approximations that we used are not enough to consider A equals 0, because higher order terms now are important. So let's put a couple of examples. First, which describes this type of behavior. So the example. So the first example is linear oscillating. Linear oscillating in general, what we consider mechanically will be a mass with a spring. So what it is, you consider some wall, and then there is a spring attached to a mass, which moves freely in direction x. So there is mass m, there is a stiffness coefficient k, and we assume that the x0 is a position at rest where the spring is not forced, and then you have a potential and kinetic energy is a standard thing, mass velocity by 2, and potential velocity of the spring, when I already told you this k over 2 by the square distance from a rest. Now you see why x minus x0 squared is exactly to satisfy the equilibrium condition. The derivative should be 0. And this is just second term. So that's nothing else as a Taylor expansion allowed equilibrium, and then neglecting the rest. So this is Hooke's law. It's very naturally appearing from any formulation that if you consider small deformations. So small deformation also have this form because it's a Taylor expansion. So what you have then is that equation of motion, it's mx double dot, and then from this to Euler Lagrange. So Lagrangian function is t minus u, equation and the equation of motion, which will be d dt dl dx dot minus dl dx. You find, you can see that it's x double dot plus k x minus x0 to 0. Or we can write it in delta x double dot plus omega squared delta x equals 0, where so delta x is distance to equilibrium, and omega squared is k over m. So you have a situation A. Right? So we have a situation A, which is tells you that in a phase space, all the motions are ellipses around x0. So whatever position you put, spring will oscillate, always coming to the same point, moving along the ellipse in the phase space. It's trivial and most canonical example. So the second example will be pendulum, which you just asked before. So what we have a pendulum, there is this support with attached mass. We consider angle as generalized coordinate, and there is a gravity force. So in that case, kinetic energy is ml squared phi dot squared over 2, because L phi dot is velocity. Absolute value of the velocity. And then potential energy, remember it's mg by height of the pendulum, and that's mg 1 minus cosine, or L 1 minus cosine. Okay. And remember that you was coming to the finally to the equation of motion. So Euler-Lagrange equation gives you phi double dot plus j over L sine phi equals 0. This was an equation of motion. Good. So how we proceed? So first, let's consider the potential as a function of the angle. And we will consider between minus pi and pi, because then it continues periodically. So that's where the angle changes. So what you have is that potential is this, you see, 1 minus cosine. So at phi equals 0, it gives you 0 with a minimum. And then it's, okay, and gives you maximum pi, and then it continues periodically. Right. So there is a minimum at 0, maximum at pi, and minus pi. So this is the lower position, right? And this is upper position. Inverted. And you see that at this point, so when phi equals 0, what is the derivative is 0, right? First of all, derivative is what? It will be mgl minus with minus, so mgl sine phi. So derivative is 0. So it's equilibrium. So vertical position equilibrium. And the second derivative so you can differentiate again. So it will be mgl cosine phi, which is mgl is positive. So it's stable situation. Right? So what you have is that what you have on the phase plane, which is angle and velocity, at 0, at small motions will have they'll move around the circle. So that's a pendulum near the local vertical position. It moves approximately along the ellipse, just in the same way as the linear oscillator. And you can check that velocity is exactly this coefficient. For frequency is exactly this coefficient. The squared frequency is J over L. So that's stable equilibrium. So now let's consider the second one at pi. Positive, negative is the same thing. So this is a motion near the inverted position of the pendulum. So derivative, you see it's sine, right? So at pi it's still 0. So it's still equilibrium. So if you put pendulum in the vertical position, it exactly should stay. And the second derivative it's cosine, but cosine at pi it's -1, so it's negative. So that so it will be that sigma squared, which is what 1 over m. Okay, not thinking. Forget about this. So what we have then? What we have is that this situation is unstable, and on a phase plane around the point P, you have this situation. So what this situation means is that, for example, this curve means that I put my pendulum, for example, right here. So at 0 speed, but slightly moved to that side. I slightly moved on the left-hand side and considered bigger than p. And velocity 0, slightly moved on that side, and then it will just fall away along this curve. And here what it means is that, for example, I can put it straight. No, right here. I can put it straight, but with the velocity slightly positive. Then it also will fall. Right? So that will be this curve. And these two straight curves, which we will consider next, are the curves which kind of at the pendulum which starts or ends exactly at the vertical position with 0 speed. Okay? Because every of these straight lines, it ends or starts exactly at the equilibrium. So we will consider separately these situations, which are very important and interesting. So that's two equilibria: vertical or inverted. Equilibrium, vertical is stable and it oscillates. Inverted, it's unstable. And we know that whenever you put small oscillations, this will be how it looks like. So I think we don't have much time. So what we do at the last moment, I will. So we have to end up with complete understanding of this situation. But so the last step we do for today is let us consider a stable motion, so periodic motion. So for example, oscillation around a stable equilibrium. Let's consider any motion which is stable. So there is a closed curve. We know that it's very natural to have a closed curve, even if we are not that close to equilibrium, because this is all this curve is this cross section of the energy surface. So energy. So in general, you have energy, which depends on velocity in position. It's certain surface, and if we start with initial condition which cuts this surface at the closed line, then this will be our orbit on a phase space. Right? So just project it. So let's assume that we will have periodic motion, which so let's find a period. So what means periodic motion? Periodic motion means that position at any time is the same as the position after a period. For any time and some fixed t positive, which is period. Period. So that's a notion of periodic motion, and every energy level which gives you the closed curve will give you the orbit on a phase plane, which will be closed. And it's, of course, periodic motion, because starting at any point, you come back to that point, and then it's start again, because the equations are all the same. So let's find a period. So what is a period? So how to compute a period? So let's write a formula for it. And let's write a formula which is not approximate but exact. You can then make approximation as well. So so we start with the energy. So I already said that this periodicity it originates with the fact that we have energy conserved. So energy, which is function of coordinates velocities, is m x dot squared by 2 plus u of x. And this is conserved, right? So equal, so let's say E constant. So constant energy defines this curve. So whenever we have a curve, we know that energy constant. So giving this value, what we can do is we can express velocity from this expression. Remember, you put u on the other side, multiply by 2 over m, and take square root. So it will be 2 over m e minus u of x. And this is square, so we take cubic root, and the sign is arbitrary. So it's clear that velocity is positive here. So this is the part which corresponds to. So this is exactly formula for this curve. And you take plus on the upper side and minus on the lower side. Just because x dot is positive here and dot is negative there by the definition. And then what you can do, you can remember that x dot is a dx dt. So we put dx on the other side and the square root below. get is dt will be dx plus minus okay. So the next thing is repeat this plot. So we have some periodic motion, maybe even not so exactly elliptic. Let's define the limiting points. So x1 at the left, x2 at the right. So it's it's certainly symmetric, right? Because the curve is completely symmetric with respect to change of sign of x dot. So it's symmetric, so it has a leftmost point and a rightmost point. Now also we know that this part is with a plus, is symmetric to the plus with part with a minus, just going to the backward direction. So it means that the period is 2 times. So we have first point, end point. So let's consider the upper part, which goes from point x1 at time t1 and reaches the rightmost point at x2 at time t2. So the time which it travels from left point to right point is t2 minus t1. But it, due to the symmetry, it's the same time as it travels backward to the origin point, so that's why I can just put 2. Okay, now we consider the upper part, so we can stick to the plus sign. So here we can take just plus. And this difference is twice integral between first point and the last point dt. So now take dt here. From this expression with plus. And it's from first point to the last point. So here we change coordinates to x, so it's from the left point to right. And that's a result. So we found that you can find the period just by integrating this expression where you only need potential energy. Integrate it between left point and right point, left point and right point of this closed loop, and multiply by 2, you get a period. So this is expression, exact expression for the period of oscillations around this curve. And if you like, you can take for example, well, this can be exercise for you. That's not the exercise. Which exercise I put along the lecture, it's not for to write and send, but that can be interesting. So you can find period for the linear oscillator. When u, remember, is k over 2 u squared. So you can take the linear oscillator where the curve is exactly ellipse and just find what will be the period. You have to substitute it here. There will be some sophisticated integral, but then either you did calculus very well and you know how to take them, or you just take a table and find what is the value with some modifications, and then you find the period. So you find the period depending on energy. So it's essentially the final formula is how the period depends on energy. So whenever you have initial condition, you compute energy, put it here, integral gives you a period. Okay, so there are a couple of things left. So we understand periodic motion. We still don't understand very well what happens here with these straight lines. So that's next question. And then after understand this, we can just draw what is the general motion for arbitrary potential. So for having arbitrary potential function, how the general motion looks like on the phase plane, and this essentially closes the topic of how the system with 1 degree of freedom moves, which is, as I mentioned, is essentially the only situation we can describe in the descending general. Already 2 degrees of freedom or more have questions which we don't understand completely, but we understand oscillations. So that's what I will proceed. So see you tomorrow. Thank you. Yes.
I didn't understand why the period is 2 times 2 minus.
Because you see because everything, you see energy and actually equation of motion, they're completely symmetric with respect to derivative, plus or minus. So what the motion above is exactly the same as the motion below, just by flipping, which means that the period which is time when it makes a complete loop is the same as the period. It has 2 parts: the time which is traverses the upper loop, and then time traverses the lower loop. But these times are exactly the same. Okay. So that's why I put 2, and only compute the upper part. So that's simply you can do compute. You can make, because the upper part is the integral with plus, that integral with plus, and lower part is that integral with minus, and they're the same.